All right, let's just jump right in with a definition. An orthogonal basis is an orthonormal basis if each vector, call it U, is such that the norm, or the length of U, is 1. All right, so let's say we have an orthogonal basis. Every pair, when you dot product it, it will get 0. It's an orthonormal basis if it's both orthogonal and every single vector in the basis has length 1. Okay. All right, so let's look at our previous example that we had. I'm going to put it back up here. We found an orthogonal basis, V1 and V2. So let's first look at V1 and look at the norm or the length of V1. Remember, that's the square root of each component squared. We get the square root of 5. So this is not a unit vector. But we know exactly how to turn something into a unit vector, right? I'm going to call it U1. We just divide by the norm and multiply by the original vector, 1, 2, 0. And so I get 1 over root 5, 2 over root 5, and 0. So this is the unit vector in the same direction as V1. And we're going to do the same with the second vector in our orthogonal basis, V2. All right, so the length of V2 is 2, and I want to normalize it. So I'm going to call it the normal version U2. So 1 over 2 times the original V2 is 0, 0, 1. Now these unit vectors are also going to be basis vectors for H. So not only are we able to find an orthogonal basis, we can also find an orthonormal basis. Okay, so we can say an orthonormal basis for H is these two vectors. Okay, so that was one big example. I want us to do one more practice with Gram-Schmidt, the Gram-Schmidt process, when we have more than just 2 vectors, because it gets a little more tricky or a little more involved when you have more than 2. So we're going to do an example with 3 vectors, 3 basis elements. So here's the example. Let's find an orthogonal basis for H that has basis so these are going to be in R4. So 3, 1, negative 1, 3. Negative 5, 1, 5, negative 7. 1, 1, negative 2, 8. All right, so these are our regular basis elements. So let me just rename them x1, x2, x3, just so we have something to call them by. And so we're going to use the Gram-Schmidt process to convert into an orthogonal basis. So remember, the first step is just using the very first basis element. So our v1 that we're looking for is going to be the same as x1. So the first step done for us, easy peasy. All right, then we have to do a little bit of work for the next step. v2, we have to use the projection. So it's going to be x2 minus the projection of x2 onto the first one, right? Because we want to create these two to be orthogonal, so we want to project onto the first one. So we're going to do x2 dot v1 over v1 dot v1 times v1. All right, so here's our x2, and then we want to subtract, so we need to do our dot products, x2, v1, so that's these two. I'm getting a negative 40, and then v1 dot v1 is 20, and then times v1. Okay, so that gives us 1, 3, 3, negative 1. So this is the second element, the second basis element. These two vectors are orthogonal, and that's what we want. And then finally, we need the third one. All right, so the third one is going to take a little bit of thought and a little bit of work to figure out what we're trying to do here. So I'm going to do a quick little note before we get into it. So note the span of x1 and x2 is the same as the span of v1 and v2. So even though we're using different vectors, these represent the same spanning set. They give you the same vectors. So what we're going to do is we're going to let h2 equal the span of v1 and v2, because we now want to think about them as a unit together, and we want to come up with a third vector that is orthogonal to both of these as a unit. So here's what we're going to do. To get our third orthogonal basis element, we're going to take x3 and we want to do our projection, but we want to project onto the whole subspace of these two vectors together. So we want to project onto h2. So we're projecting x3 onto that subspace. And we have to remember, well, how do you project onto another subspace? We have to project onto each component separately. So this is x3 minus. All right, so we want to project onto v1 first. So x3 v1 over v1 dot v1 times v1. Then I'm also going to subtract the projection onto v2. So we got x3 v2 dot product over v2 dot v2 times v2. All right, so it took a little more work, but we're just doing it component-wise. All right, now we just use our vectors. So first we need our x3, which is 1, 1, negative 2, 8, minus, we need our dot product here, that's 30, over 20, times v1 minus, then we need our dot product here with the last one. That's going to be negative 10 over 20 times V2, which we found. And then what do we get when we put it all together? I'm just going to spoiler get the answer. Negative 3,113. So now we have an orthogonal basis for H. All right, so it's our V1, our V2, and our V3.